Hello everyone, welcome to my AAAR poster booth. I'm Chenchong from Washington University in St. Louis. My research is to assess the polarimetric measurement sensitivities to light-absorbing aerosol. The radiative forcing contributed by aerosol in the atmosphere includes their direct radiative forcing and cloud adjustments. The overall direct radiative forcing of aerosol is resulted from the negative forcing from most types of aerosols and the positive contribution from light-absorbing aerosols. Compared to other types of emissions and climate drivers, aerosols continue to contribute the largest uncertainty to the total reflective forcing estimate. The uncertainty of radiative forcing estimates of aerosol is partly attributed to a wide range of the aerosol's macrophysical properties. The upper left figure from the in situ measurements shows the time series of the values for imaginary refractive index of brown carbon measured by a photoacoustic instrument. Shaded area illustrates a large propagated uncertainty of brown carbon's refractive index, which ranges from less than 0.01 to 0.06. The lower left figure adapted from the same study shows the fractions of externally mixed primary particulate organic matter, or POM in abbreviation, during the continuous measurements. Different areas bounded by white vertical lines illustrate the periods of two biomass burning events and the background conditions. The comparison between BB1 and BB2 prove the emissions from two biomass burning events are with different mixing states, even if they were happened in the same location. Besides the particle refractive index and their mixing states introduced in these slides, particle sizes, particle shapes, their vertical layering, and plume height can all affect the optical signals detected by remote sensing sensors. Among all types of measurements, satellite remote sensing have made it possible to retrieve aerosols properties from airborne or satellite platforms from a regional and global coverage. We show an example here. The different pixel color in the left figure shows the different types of aerosol classified based on two satellite products. MODIS and these two satellite products are MODIS and OMI. And the classification principle is based mainly on aerosol sizes and the refractive index. The left flowchart illustrates this principle. As illustrated in the table on the right, MODIS and OMI measured radiance as specified single viewing angle, and the measured radiance is the integration of the scattered light from the entire atmospheric column. The number of required aerosol parameters obviously exceeds the number of observables from these sensors. So to produce better retrieval accuracy, recent algorithms have shown a progressive trend of including multi-angular, multispectral polarimetric satellite data. For example, MISR, or multi-angle imaging spectral radiometer, developed by NASA and JPL, and also polarization and directionality of the Earth's reflectances, or POLAR in abbreviation, developed by French Space Agency, have both incorporated such functions into application. MISR has an angular coverage between 70° forward to 70° backward for 4 wavelengths, and an airborne version of MISR sensor known as Airborne Multi-Angle Spectral Polarimetric Imager, or RMSPI in abbreviation, has a similar angular coverage as MISR, with an 8-band ranges from 355 to 935 nanometer. Besides the radiance measured at all 8 bands, it also measures polarization signals in the 470, 660, and 865 nanometer bands. Our study mainly focused on the wavelengths and viewing angle RMSPI sensor can cover. Aerosol retrieval algorithms utilize the remote sensing data to study aerosol properties. In practice, we need to choose the most cost-effective data among multi-angle and multispectral datasets for efficient aerosol retrieval purpose, or in other words, to find the optimal configuration of spectral wavelengths and viewing angles for light-absorbing aerosols we want to study. This research objective is related to the first step of development of an aerosol retrieval algorithm, which is generating a synthetic dataset from the forward radiative transfer simulations for a wide range of aerosol macrophysical properties. Yeah, this is the first step as shown here. And furthermore, a retrieval algorithm is the inverse problems of the first step radiative transfer simulation. In our current research, we will not evaluate the retrieval quality. This slide shows the general method of this study. It splits into three major parts. We calculate the optical parameters of particles through means theory. In this part, we mainly adjust particle sizes and refractive index to obtain optical properties of different aerosol groups. We concern about three major optical parameters: aerosol optical depth, single scattering albedo, and phase matrix elements. The aerosols are well mixed with background atmosphere to formulate the aerosol mix layer. We also add a reflectance surface at the bottom of our simulated system. Then we use a vector radiative transfer model based on successive order of scattering principle, or SOS in abbreviation, to calculate the remote sensing responses at the top of atmosphere. The first step of the final step of our study is to apply Jacobian sensitivity analysis upon the polarimetric remote sensing signals we obtained in the second step. The particles are assumed to follow monomodal log-normal distribution for all parallel simulations. The probability density function of log-normal distribution is shown here. There are three parameters need to be defined in this equation. So first, we fixed AOD, which constrains the total number concentration. And we fix AOD at 1.0 as a representative of high level of particulate pollution. And standard deviation value chosen here is an approximate estimate of different particle mode based on the previous aerosol retrieval results. It is 1.6. So we only change the values of geometric mean radius to obtain different particle size distribution. And furthermore, by using mean theory, we can calculate their SSA and the related phase matrix elements. The vector radiative transfer code we used here is based on plane parallel successive order of scattering, or SOS in abbreviation. And we calculate the angular distribution of the polarized radiance scattered by the simulated atmosphere-ocean system. From bottom-up direction, it is the oceanic surface, 2 kilometers high aerosol mixed atmospheric layer, and a pure relay atmosphere. Reflectance quantities at the top of atmosphere are affected mainly by the properties of the aerosol embedded atmospheric layers. The viewing geometries of SOS model includes the azimuthal angles and the zenith angles. They are illustrated in the red figure. The solar zenith angle theta 0 and the viewing zenith angle theta v are measured from the vertical z-axis. In practice, the relative azimuth angle phi, which is defined as the angle measured clockwise from phi 0 to phi v, is the direct input parameters of SOS code instead of phi 0 and phi v. The scattering angle, which is highlighted in the red box, has been calculated based on three angles mentioned above. The viewing zenith angles are consistent with the angular detection limits of our MSPI sensors. We selected the different viewing geometries to acquire a wide range of relative azimuthal angle, and our angle selections ensures to acquire an increase in scattering angles. The resulted scattering angles ranges between 80 degrees and 178 degree. We have defined 4 types of light-absorbing aerosol based on their different refractive index. As shown in this table, we have 2 types of black carbon aerosol with strong light absorbing and organic carbon with weak light absorbing. The refractive index of these 3 types of aerosol are spectrally independent. In contrast, we assume the refractive index of brown carbon is wavelength dependent. It significantly absorbs light in ultraviolet, too short visible wavelength regime. The figures in this slide shows the phase matrix elements F11, F12, and the ratio negative F12 over F11 of the 4 types of light-absorbing aerosols at 3 studied wavelengths. Figures in the same columns are phase matrix elements at the same wavelengths. So we can draw several conclusions from these slides. Firstly, F11 values of brown carbon and organic carbon have peaks at backscattering directions. And second, F12 values of all types of aerosols are close to 0 as scattering angles exceeds 90 degrees. And negative F12 over F11 ratio of light carbon particles have peaks at 90 degrees, while brown carbon and organic carbon have negative peaks at 150 degrees. And differences between 4 types of aerosol tend to decrease as incident wavelength increases. So the phase matrix converts the incident Stokes parameters into the scattered Stokes parameters. The values of the matrix components indicates the optical properties of the aerosol mixed atmosphere. We further studied the effects of the particle phase matrix on remote sensing signals. Here we firstly define 3-dimensionless reflectance factors, bidirectional reflectance factors or BRF in abbreviation, and polarized BRF, and also degree of linear polarization or DOLP in abbreviation. Note here the magnitudes of BRF, PBRF, and the DOLP at a specified scattering angle, by their definition, can be thought of to be proportional to the F11, F12, and the negative F12 over F11 values, respectively, and which we have mentioned in the last slide. In this slide, we show the simulated polarization signals and the reflectance factors at the top of atmosphere. Among 3 reflectance factors, BRF and DOLP show similar angular dependencies as F11 and negative F12 over F11, respectively. And comparisons between BRF, PBRF, and DOLP show that PBRF has the lowest magnitudes among 3 reflectance factors, and also the reflectance factors of BC high are similar to BC low. This similarity also exists between brown carbons and organic carbon. And the largest reflectance factors differences between different aerosol types are observed at 470 nanometers at a scattering angle close to 90 degrees. So in the following analysis, we just focus on the shortest wavelength, 470 nanometers. And because of the similarities between 2 types of BC particles and also brown carbon and organic carbon, we only show phase elements of BC low and brown carbon here. The comparisons between BC low and the brown carbon show that brown carbon and the black carbon have different angular dependencies of F11, F12, and negative F12 over F11 ratio. And for each type of aerosol particles, size affects the magnitudes and angular dependencies of phase matrix elements, especially at the near the backscattering directions. So the further radiative transfer simulations show the polarized reflectance factors P, BRF, and DOLP They have low signal magnitudes in the near backscattering angle range. The difference exhibited in the phase matrix elements doesn't lead to much differences in the reflectance factors. And also from a perspective of getting higher signal to noise ratio, large scattering angles are not preferable. Hence, our further analysis was applied at a scattering angle of 81 degree and incident wavelength of 470 nanometer. We have extended the reflectance factor calculations into a continuous spectrum of particle size and reflective index to find the most sensitive region for particle macrophysical properties. We find that the BRF is mostly sensitively affected by size at small refractive index region. Also, in the same region, refractive index effects itself is also prominent. In contrast, PBRF has a low signal magnitude for the entire size and refractive index ranges. In contrast, DOLP have the higher signal magnitudes and the larger value range than BRF and PBRF shown in the last slide. Not like BRF and PBRF, the high magnitudes of DOLP generally appear in the large size region. Those large DOLP values are resulted from the collective effects on polarization between relay atmosphere and strong light-absorbing aerosols. For weakly light-absorbing aerosols, brown carbon and organic carbon, which is highlighted as the left area bounded by a black arrow in figure A, the decreasing trend of DOLP with the increase of effective diameter holds for small particles. As the size continuously increases, DOLP is nearly constant for wide size range. This result is consistent with the negative f12 over f11 ratios we illustrated before at the same scattering angle. Sensitivity of DOLP to imaginary refractive index is also quantified through the finite difference form of Jacobians in figure B. For all studied particle size distributions, Jacobians of the DOLP show prominently high values for particles with extremely weak light absorption. The insight of figure B shows the Jacobians of DOLP for two size distributions with the smallest and largest effective diameters as refractive index exceeds 0.1. It proves the DOLP sensitivities to refractive index are also affected by particle sizes. Small particles have larger sensitivities for the relative change of refractive index values when it is less than 0.4. This indicates that in the retrieval algorithm, the measurements of polarization contain more size information for refractive index values less than 0.4. So here is a kind of a conclusion of my research. The computation through me code shows weakly light absorbing brown carbon and organic carbon have distinct phase function f11 and degree of linear polarization negative f12 over f11 patterns compared to those for strongly light absorbing black carbon aerosols. The difference is most significant at an incident wavelength of 470 nanometer than the cases of two longer counterparts. We applied the optical parameters of different types of aerosols mentioned above into the SOS algorithm to calculate BRF, PBRF, and DOLP at the top of atmosphere. The angular dependency of of BRF and DOLP follow the similar changing patterns of f11 and negative f12 over f11 ratio respectively. The angular dependencies of PBRF are mainly determined by relay scattering of atmosphere because of the low magnitudes of the polarized phase function f12 of particles. And all three reflectance factors have the higher magnitudes and sensitivity at a scattering angle near 90 degrees. And the comparisons of the reflectance factors between strongly and weakly light-absorbing aerosols indicates their different levels of sensitivities to effective diameters. Fluctuations in the values of the particle imaginary refractive index and the effective size within the low refractive index region will more effectively influence the magnitude of BRF and PBRF. And finally, DOLP, which is defined as the ratio of PBRF and BRF, amplifies the sensitivity to both refractive index and effective size. In this study, DOLP ranges widely from 0.23 to 0.88 at a scanning angle close to 90 degrees. It is most significantly affected by particles' refractive index values in the weakly light absorbing region. Quantitative sensitivity analysis shows particle sizes influence the level of DOLP sensitivity to refractive index. The results indicate the polarization measurements contain more particle information when refractive index is less than 0.4. The next step of our research is to quantify the aerosol macrophysical property sensitivities over various polarized surface and a mixture of different types of aerosol. We will also address the question of retrievability of these key aerosol properties with multispectral as well as multi-angle photopolarimetric data. And thanks for your attention. You can visit our group website for more information.